So, welcome back to our video lectures on projective geometry. This time we will be very geometric. We will speak about so-called harmonic sets and quadrilateral sets, which are special configurations on the projective line that play a very important role all over projective geometry. Let's right away start with the take-home message, and the take-home message is that whenever you see one of those pictures here, you should immediately being able to associate them with quadrilateral sets and harmonic sets, and that you should be able to recognize these pictures as sub-configurations in other incidence situations, because we will need them over and over again in what follows. So you see these yellow lines here in each of those drawings, and those yellow lines here should represent a one-dimensional projective space or one-dimensional projective line, and essentially we are talking about certain configurations of points on the projective line that are defined by, well, essentially other configurations in a surrounding space that somehow relate to them. And what you see here in that picture is a so-called quadrilateral set. What you see in that picture here, it looks completely different from the first one, but the point configuration that you get is essentially the same. So you have also a quadrilateral set. And here in the last picture, well, the main difference from here to here is that some of the points start to coincide, and what you have here is a so-called harmonic set. Each of those configurations has a nice characterization via determinants in the projective line. So if you look at the first thing, it is characterized by the following property: a product of certain three determinants minus the product of other three determinants should be 0. The second one, well, it's the same set, it has the same characterization, is characterized by the same equation, and the last equation is characterized by this equation here. And it turns out this is nothing else that as a certain cross ratio being -1. So let us start with the seemingly most complicated figure on that page, and let me explain what's going on there. So it's called quadrilateral sets, and in quadrilateral there is this quad inside, and this means somehow a 4 is involved in one or the other way. And the way the 4 is involved in that picture is that you start with a configuration of 4 more or less arbitrary line. More or less arbitrary, again, things should not be so degenerate that lines coincide. So you start with 4 lines such that no 2 of them coincide and that no 3 of them go through a common point. If you do so, then, well, by the projective geometry axioms, each pair of such lines has a unique point of intersection, and since you have 4 lines, you get 6 points of intersection. And now we do the following: we take a line and project those points down on that line and form the 6 points of intersections, and we are interested on the relation of those 6 points. And well, what happens? Well, one question is, you may consider this as a kind of shadow. So assume you have a light source far out in that direction and it projects down, and so these green points here are the images of the red points here. And one question is, how freely can this shadow move if you just know about the configuration what I now told you. And the amazing fact is that the position of already 5 points of this configuration determines the position of the last one. We will see how that works in a minute. And so I first want to exemplify why the last point is already determined. So assume for a moment we only know the position of the shadows, and we want to reconstruct the lifted configuration here. So we may say, well, start with an arbitrary line and form the first 3 intersections here. So actually, so far without loss of generality, we could have chosen really any line, at least as long as it's not vertical, because by projective equivalence we could move any arbitrary line to any other. So we start with an arbitrary line, and again without loss of generality we can fix 1 point on that line, but from now on everything is pretty rigid. So in our configuration we also had this line here, and well, if we have this line, then the intersection of point D with projection of the shadow is uniquely determined to be at 1 point. And then, well, we in addition also had this line and this line, and now something interesting happens. These 2 lines have a point of intersection. So if you did this construction, it turns out that, well, after you've chosen your points here, this point here is already at a fixed position, and so the position of F essentially is determined by everything we did so far, and there's no freedom in the choice of F. Well, really no freedom? We had some smaller choices here. So we choose the first line for free, and we chose this point for free. And maybe this freedom allows us to move that point here to different situations. But we will see in a minute that exactly this is not the case. And the important thing here is that we now do an algebraic calculation that helps us to understand what's going on. And for doing that algebraic calculation, I want to have my things as simple as possible. And here I've written the whole situation up here is invariant under a shear along the projection axis. So without loss of generality, I could move my configuration such that, for instance, the line ABC becomes parallel to my yellow projection line. Let me just do that here. So not much has changed, and we are still in the fully general situation. And now we will start to calculate. And how will we start to calculate? We consider it as a kind of reconstruction problem. So what we take is we take the position of those points, and we want to reconstruct the position of the red points over here under the assumption that we have those collinearities here and that we have the orthogonal projection. So essentially we have to determine heights of each of these points over the yellow axis to find out where these points lie. So we want to get these heights together with some kind of side constraints. So well, the first observation is, so our unknowns are those heights here, and the first observation is, well, we could still move everything up and down and wouldn't violate any generality. So we could say, well, if we are looking for certain heights, we may assume that this line here is leveled to be at a height of 0. So we assume these points here are sitting at an altitude of 0, which essentially simplifies our formula here. We get many zeros in here. So we still have to determine what are the heights of point D, point E, and point F. And we have to satisfy our side constraints of all the collinearities. One of those collinearities we already satisfied by putting all these lines to a height of 0. So A, B, C are automatically collinear, but we still have to make sure that A, E, F, that B, D, F, and C, D, E are in a collinear position, which could be considered to be condition of a determinant vanishing. You may observe in my matrix that I took a slightly non-generic way to make the standard embedding. So I put the ones for the standard embedding in the second row. The reason why I did that is that I wanted to have my heights here, my altitudes, at a special position. So, but we think of those points embedded in the standard embedding with, well, the x-coordinate is essentially A, B, C, D, E, and the y-coordinate is what's happening down here, and the embedding coordinate is this one. So, we want to satisfy this choice of coordinates. We don't know HD, HE, and HF yet, but we want to satisfy those constraints as well. So let's have a look at those constraints. They are, again, determinant conditions. And, well, I've written down the determinants here. So I used the, vertical bar notation for determinants. And if you look at, for instance, A, E, F, you have point A, you know, there's a height 0 involved here, point E and point F, and the determinant of them has to be 0, and so on and so on. If you look at those determinants, you recognize that you have a 0 in the first spot, which really simplifies the algebraic expression. So each of those determinants can be simply written as such an equation where I have written AF to be the 2 by 2 determinant of 2 points, and AE also to be a 2 by 2 determinant. So if you look here, the AE should just be this 2 by 2 determinant, and I've written it as a 2 by 2 matrix, indicating that we are actually at that point here living in a one-dimensional projective line for those points. So, how to continue? Well, we want to satisfy all three equations that we have here at the same time. So if you look at them, you notice that all the altitudes here occur linearly in these expressions. So if they occur linearly, we can write down a linear equation. And the linear equation we get is this one. We need that matrix times the altitude vector, and all these equations have to be satisfied. So we get zeros all over there. So our entire problem at the end boiled down to the question, does this system of equations here have a non-trivial solution? Non-trivial solution here means that we get something else than all heights being 0. Okay, you're looking for a non-trivial solution of a linear equation system that should evaluate to 0 at the end, and there is a nice criterion coming from linear algebra to make that, to decide whether this is possible. You only have to look at the determinant of that matrix. This matrix has many zeros, so the determinant is a pretty simple thing, and in that case the determinant of that matrix ends up to be this expression. Let me summarize. What did we do? So we started with this configuration here of points. we wanted to get some lifted points A up to F, satisfying these collinearities. We made some reasonable assumptions that we can do without loss of generality. We encoded our collinearities, this one, and this one, as determinant expressions. We wrote down these determinant expressions in the variables. We found out that we have a linear equation here, and we are looking for a non-trivial situation of the linear equation, and we found out that exactly this condition has to be satisfied to have this non-trivial solution. So, in other words, our points here can only be lifted if our points satisfy this equation, and this is really a nice condition independent from our lifting. So we can state this condition here purely in terms of our one-dimensional space we have sitting here. So 6 points are in a position such that they can be lifted if and only if this equation of determinants here is satisfied. We call such a set of such a collection of 6 points that satisfy this relation a quadrilateral set, and you should notice that the points play a slightly unsymmetric role. There is not the full S6 working as a permutation group here. So actually a good way to write that down is to say that A, D here, B, E, and C, F from a quadrilateral set, where I said this pairing here comes from those points that are not connected by a line. So you see A and D is not connected, B and E is not connected, and F and C is not connected. There's another way of writing that. We could shuffle around our equations a little bit and write it as such a kind of expression, and now some of your recognition bells should ring. You see this expression and you should immediately notice this is a projectively invariant function on 6 points in the projective line. So this part here doesn't change under projective transformation and rescaling of the representatives, because each letter happens to be once in the above expression and once in the below expression, and you have the same number of determinants, and so the same reasoning that we did before for projective invariance applies here as well. So we don't even have a characterization for this orthogonal projection. Everything we do is now projectively invariant, which means the same reasoning would also apply if we wouldn't do orthogonal projection, but if we would do a central projection. So this knowledge that this is the same construction or the same condition somehow comes in an a posteriori way. So after we see this equation, we see it is projectively invariant under our usual transformations, so it must also characterize this situation here. So let me go back to our original picture, and I want to show you something else that happens here. So if I called it quadrilateral set, and I said in some sense the number 4 has to be involved here. So we have 4 lines and 6 points. And so far everything we had in projective geometry was such that points and lines somehow played an interchangeable role, and actually the same happens here as well. There's also a configuration of 4 points and 6 lines that gives the same points, and what you get here is, well, now you don't start with 4 lines, but you start with 4 points. Instead of forming all points of intersections, you form all connecting lines and intersect them with our yellow line, and you again end up with a quadrilateral set. You could argue that this is the case by duality. Since we didn't have a proper notion of duality yet, I want to show you that this is the same thing by just a different consideration. So let us start with our picture once again. And I said without loss of generality, I could make this line and this line here parallel. So if they are parallel and we don't care about shifts in that direction, we could even say, well, let's go one step further and identify those two lines. We learned that things are projectively invariant, so instead considering central orthogonal projection here, we could also consider central projection and end up with this picture and still have a quadrilateral set here. But if you now look at that picture here, you recognize you have 4 points and all connecting lines and intersect them with a line. This is exactly what I've gave you before as this dual characterization of a quadrilateral set. So let me go back to my situation I had in the first picture. Let me switch back colors. So this is our second characterization. So we have seen 2 entirely different characterizations related by duality for quadrilateral sets. So now let me do one more thing. Let me move my points a little bit around in a way such that these 2 points coincide here. And here I've written down, well, this is a so-called harmonic set, and it's characterized by a condition for a cross ratio. And let me see how to get from this formula here to the formula here in the cross ratio. So I identified some of the points. So I said E and B should be the same point, and C and F should be the same point. So I have my equation over there, and now I say B and E are the same and C and F are the same, so I can just use one letter for them. If you look at that expression here, you find out that, well, here you have a term BC and you have a CB, so assuming that those 2 points don't coincide, so again everything should not be too degenerate, then you cancel out that term. And you have to be a little bit careful. The order of the terms here brings a little minus sign when you cancel, and so shuffling those terms and canceling out brings you to this expression here, which is nothing else as a certain cross ratio being -1. In that situation, A and B play the role of one of the pairs, and C and D play the role of the other pair. So you see, harmonic sets could be considered as a kind of special case with coinciding points of quadrilateral sets. And you also see, well, harmonic sets can nicely be characterized by cross ratio being 0. And those of you who attended my Geometriekalküle lecture will remember that, well, harmonic sets played a very important role there. One of the reasons they played an important role there was the following fact. Well, if you move one of those points in harmonic sets to infinity, so one of those points, point C, has been moved very far out, then what happens is that you get the same distance between A and B and D, which means that B turns out to be exactly in the middle of A and D. So harmonic sets can really be used to construct midpoints in the standard embedding in a purely projective manner. So let me end this lecture by, well, a little dynamic picture and exercise. I just want to show you how to construct a point in the quadrilateral set if 5 of the other points are given. So as a kind of reference picture, I've drawn the picture we had before over here, and now we have essentially the same situation. We are given point A, E, B, D and C, but the position of point F is still missing. So how do we construct point F? Well, we just have to redo that construction, and everything I told you so far well, makes it sure that no matter how we redo this construction over there, we will always end up at the same position for point F. So what do we have to do? First thing, we have to add one auxiliary point which plays the role of this point here. After we added that point, we have to connect it to 3 points. We have to connect it to A, D and C, and this is what we do next in our construction. So we take that point, connect it to E, connect it to D and connect it to C. So we got 3 lines of intersection and 3 lines that join, and well, the other 3 points here are still missing. So we start with one arbitrary other point, say this one here, and add it into our construction. So here is this point on the line that goes through C, and now this point has to be connected to A and to B. So let's do exactly that. So here we take that point, connect it to A and connect it to B, and after we did that, we get those 2 intersections here, which are the positions of the other 2 points. And so we place points at those intersections, and finally we have to connect them and use the connecting line to intersect with our yellow line to get the position of point F. So here we have the connecting line. The only thing that's still missing is the intersection with our yellow line, and we get the position of point F. Important fact, we would always get the same point F no matter where we chose the auxiliary points. So let me move those auxiliary points a little and observe the point F here. It was completely dependent of our construction, but its position simply doesn't move. It's completely independent from the rest of the construction. The only thing it depends on is the position of all the other green points. So if I start to move the other green points, you see point F moves immediately. So this concludes our little excursion on harmonic and quadrilateral sets. And you will see that from now on, both these concepts will play a very important role of what is coming next. And in our next lecture, we will see that, well, quad sets and harmonic points can be used to mimic addition and multiplication of coordinates on our one-dimensional projective line. And this in turn will later on lead to the fact that if we have projective geometry that satisfies certain incidence theorems, then from that projective plane we can reconstruct a field over which it is defined. but we will see that in one of our next lectures.